So now we're going to examine energy sources within star groups and exactly how stars form, live their life cycles and die. So some reminders first. Luminosity is the total energy radiated by a star, as opposed to brightness, which is the intensity of the light at some distance away from the star. The temperature of stars, cooler stars are red, most of the visible radiation at longer wavelength, and hotter stars are blue. If we recall the Hertzsprung-Russell diagram, it's a graph of the star's luminosity plotted against the temperature or colour. Stellar evolution. If you want to follow this, you can use page 15 in your topic notes. The life of a star follows a pattern like human life. Stars are born, they mature and they die. As they mature, they change in their chemical and physical composition. Their size changes and their energy and gravity change too. We notice radiation pressure from the energy source within needs to be balanced by the force of gravitation due to the mass of the star. So different radiation pressures depend upon which phase of the life the star is in. This is due to the different nuclear reactions within the cores of stars as they age, and these reactions change throughout the life of the star. Reactions in stars. First of all, let's look at a main sequence star. Here we have mainly hydrogen fusion to form helium, which releases large amounts of energy. As the star ages and becomes a red giant, we get helium fusion into carbon. We're still getting some energy released, but you'll note that it's not as much as in the previous reactions. In the more massive stars, we will get carbon and helium fusing to form oxygen with the release of gamma radiation. So let's have a look at those reactions. The supergiants, oxygen confused to form heavier elements such as silicon and sulfur. Eventually, after further fusion, elements as heavy as iron can be formed. This is the heaviest element that can be formed in an energy-producing reaction. There's a system of multiple shells, each with different energy source, and these can all exist at the same time. And here, if we cut a cross-section through a typical star, we can see the different layers with the different reactions taking place. With iron being the heaviest element formed, this tends to sink to the core. What are white dwarfs? Well, these are almost at the end of the life cycle of the star. There are no nuclear fusions. The star has collapsed into a corpse. There's no fuel left, no remaining energy source. They can radiate heat into space, but they cool down to become black dwarfs. So here's a table to summarise the reactions. As we can see, main sequence have nuclear fusion of hydrogen to helium in the core. Red giants, we're getting fusion of helium to carbon, with hydrogen fusion continuing in a shell. Supergiants, multiple nuclear fusions possible in shells, forming elements up to iron in the core. And white dwarfs have no energy-producing reactions occurring at all. So let's have a look at the life of a star with reference to the Hertzsprung-Russell diagram. We can see our supergiants are up here, and we've got some possible helium burning and shell hydrogen burning in our red giants. When we talk about solar masses, we refer to our own sun as one solar mass, and we compare everything else to that. And here's all our main sequence stars as we noted before, and these will all have hydrogen fusion to helium, and down here we've got our white dwarfs with no energy reactions occurring. So what are the phases in the life of a typical star? Well, first of all, a star has to be formed, and this occurs in a phase called a protostar. Then they mature into main sequence, followed by red giant, and then white dwarf. So what's happening in the protostar or nebula stage of a star? Well, it begins as a contracting gas cloud. That's what a nebula is, the birthplace of stars. There's mostly hydrogen and maybe a little helium at this point. Now, the composition of the nebula depends on the presence of nearby expired stars. You could have heavier elements present, such as lead, and if it was a supernova, then maybe as heavy as uranium could be present. Our Sun does have traces of this, and of course these have been leftover elements from the explosion of large stars prior to the formation of new ones. So a forming star is known as a protostar. The star begins to form when a gravitational center occurs within a nebula. This will be due to an unevenness in the spread of particles, with clumps exerting more gravity and attracting more atoms towards them. Gravity will then pull atoms towards the center. If the cloud becomes dense enough, gravity will collapse the cloud upon itself. Think of it as sections of a cloud falling together to form a star. The falling atoms of gas speed up as they approach the center. Gravity pulls the atoms together, they collide, and these collisions heat up the center or core of a forming star. Temperature is a measure of the average speed of the atoms in a material, so the contracting gas becomes hot. So collapse to a protostar. This will occur as the slow accumulation of gas and dust continues. Gravitational attraction of clumps attracts more material. Contraction causes temperature and pressure to slowly increase. And obviously we've seen that force exerted between two masses depends upon their size and the distance between them. So the protostar stage. Contracting nebula heats up and is called a protostar. If sufficiently large enough, the core will heat up enough for hydrogen to fuse. If it's too massive, once fusion begins, the radiation pressure will be so great that the protostar is immediately blown apart. So adding atoms to the center of a protostar is a process astronomers call accretion. Because numerous reactions occur within the mass of a forming star material, a protostar is not very stable. In order to achieve life as a star, the protostar will need to achieve and maintain an equilibrium. And what exactly is that? Well, in this case, it's a balance between gravity pulling atoms towards the center and the gas pressure pushing heat and light away from the center. If either one is too great, equilibrium will not be achieved. Achieving and keeping this balance is tough to do. When a star can no longer maintain equilibrium, it dies. So gravity pulls gas and dust towards the core, inwards. Inside, the temperature increases as the gas atom collisions increase. The density of the core will increase as more atoms try to share the same space. Gas pressure then increases because atomic collisions and density are also increasing within the same space. The protostar's gas pressure resists the collapse of the nebula, and when the gas pressure equals the gravity, the protostar has reached equilibrium and accretion stops. So what's happening in the main sequence stage? Well, once fusion of hydrogen begins, this is what we call main sequence, and the star will spend most of its life in this phase. It produces helium as the hydrogen atoms fuse. Helium settles to the center because it's denser and because the gravity therefore will pull it to the center. But eventually the fuel supply will dwindle. So what happens next? Here we just see the hydrogen atoms changing to helium. Just think about how many hydrogen atoms you would need to form a helium atom. And our own sun is in this main sequence phase right now. Next comes the red giant stage. So radiation pressure leaks out and the star's core shrinks because of the effects of the gravity. Energy is released to the outer layers, which expand, and they can expand enormously. The remaining hydrogen fusion now shifts to a shell that will expand greatly in size, cooling as it becomes less dense. A collapsing core causes sudden increase in pressure and temperature that initiates fusion of helium into carbon. This will be followed by the white dwarf stage. The core of the red giant runs out of fuel. Star contracts yet again due to its gravity, and it sheds the outer layers, losing mass. The remaining core is a star corpse, no longer performing fusion and cooling down. It has a smaller mass, it sheds layers gently as a sphere-shaped nebula, which cools into a black dwarf. It has a larger mass, 1 teaspoon of it will equal 1 ton. Sheds layers violently as supernova, as an enormous explosion, and it may become a neutron star or black hole. So what about the mass of stars? Well, note MO equals 1 solar mass. That's the equivalent of our Sun. So here we can see in this flowchart the molecular cloud condensing into a protostar. That becomes main sequence. It may become a red giant with a number of burning shells depending upon its mass. Now from this stage it's got one of 2 paths that it can follow. If the original mass is equal to about 5 times our own solar mass, you'll get a planetary nebula leaving behind a white dwarf. However, if we have a original mass greater than 5 times that of our own Sun, we will get a supernova. And this will leave behind either a neutron star with a core of about 3 times our Sun, or a black hole if the core is 3 times greater than our Sun. So mass affects the life cycle of the star. Let's compare them with humans. A protostar is like a fetus, and this can be seen here in this comparison. Then we have fusion ignition into main sequence. So that's infancy through to adulthood. When we get the red giant or supergiant, this is equivalent to middle age, and eventually we get old age and death in the form of a white star or black hole.